In this module, we are going to learn how to apply the non-parametric test in R, and initially we'll learn the binomial test, the sign test, Wilcoxon sign test, the Mann-Whitney test, Kuskal-Wallis test, and there are different functions for the different tests. We learn about the different functions that are available in R and different arguments that need to be passed through that function, through those functions. And then we will use a different data set for different type of test, binomial test and the sign test. We use one kind of data, and then sign the Mann-Whitney test and the sign Wilcoxon sign test. We will use another data to apply those functions on the data to see what are the different results that come out through that test, and then we will learn the interpretation of the different results that come from those functions. Application of the functions on the data and how to interpret those results that will come out. In this module, we'll learn different existing function for non-parametric test in R. I'll start with the binomial test, which is more relevant to the sign test, the first test that we learn in non-parametric statistics. Start with this example. Under simple Mendelian inheritance, a cross between plants of two particular genotype produces progeny, 1/4 of which are dwarf and 3/4 of which are giant, respectively. In an experiment to determine if this assumption is reasonable, a cross result in progeny having 243 dwarf and 682 giant plants. If giant is taken as success, the null hypothesis is P equals to 3/4 and the alternative is P not equals to 3/4. One can use following functions for binomial test to get the solution of the above functions. Say binom.test x in P equals to 0.5. Alternative is two-sided, less than or greater than, confidence interval 0.95 by default. You can set your confidence interval, the confidence level there. It performs an exact test of simple null hypothesis about probability of success in binomial experiment. The arguments are as follows: x, the number of success or a vector of length 2 giving the number of success and failure respectively. N, small n is the number of trial. Ignore if x has length 2. P is the hypothesized probability of success. Alternative indicate the alternative hypothesis must be one of the either 2, greater or less. You can specify just the initial letter. Confidence dot level is the confidence level for the return confidence interval. A list with class H test containing the following components, that is the value that would be returned by running this function: the statistic, the number of success, parameter, the number of trials, p-value of the test, then confidence interval, the confidence interval of the probability of success, estimate, the estimated probability of success, null dot value is the probability of success under null p, alternative, a character string describing the alternative hypothesis, method, the character string exact binomial test, and data.frame, a character string giving names of the data. All these return value can be accessed through the object of that particular test, $, the name of the parameter return value that you are willing to get. Say, and otherwise if you just run the test, it will give you all the parameters that are listed there. So binomial.test, C, the 682 and 243, P equals to 34, then it will return you the, say, data is 3 for 64, 684 and 243, N and P, N and the actual success, number of success. So number of success is 682, number of trials is 925, or number of success and number of failure is given C. So success is 682 and trial is 925, p-value is 0.3825. Alternative hypothesis, true probability of success is not equal to 95% confidence interval, and the 95% confidence interval has 0.7 to 0.76. Same sample estimates of the probability of success is 0.74 if I round it. So that's the information that we'll get from testing this function. And alternatively, you also can write, binomial test 682 and 682 plus 243, p equals to 34, and that also will generate the same results that are there. So data are in agreement with the null hypothesis. Next we will move to the sign test, that is the function called PathWR. So PathWR, not function, it's the package that you may have to download. The function is sign.test. This function will test a hypothesis based on sign test and reports the linearly interpolated confidence intervals for one sample problems. For sign.test, the arguments are x, y, MD, median value, the alternative, and the confidence interval. Say x is the numeric vector, y is the optional numeric vector, NA or infinites are allowed but will be removed. MD, a single number, represents the value of the population median specified by the null hypothesis. Alternative is the any string, any one of the alternative you have to choose. Then confidence interval should give you the, you should provide the confidence level. By default it is 0.95. So compute two-sided sign test for null hypothesis that population median is 21. The alternative hypothesis is not 2.1, and interpolated upper 95% confidence interbound of the population median will be computed. Say first I load the library PathWR, and then with data phone the sign.test call.time and median equals to 2.1, and it will generate the results, one sample sign test, and data, it will give the test statistics S equals to E, 1, p-value is 1. So alternative hypothesis was equals to 2.1, not equals to 2.1. The 95% confidence interval is given 0.75, 722, 5.49 or 5.5. The sample median was estimated as this, and the interpolated 95% confidence interval are given as follows. Now we'll see how Wilcoxon Ranksum test, or rather Wilcoxon test, any Wilcoxon Ranksum and Wilcoxon sign test can be done by the same function called Wilcox.test. So we'll see the Wilcoxon Ranksum and sign rank test by Wilcoxon.test. Perform one or two sample Wilcoxon sign rank test and Mann-Whitney test, that is the Wilcoxon Ranksum test by this function. The three way you can use this function. One is the Wilcox.test x, and other function is Wilcox.test x and comma y alternatives and others informations. Wilcox.test, you can use the formula itself. So first one is the one sample, second one is the two sample, and third one is the two sample in formula form. So x is actually numeric vector of data values, non-finite, and y is an optional numeric vector of data values. As with x, non-finite values will be omitted. Alternative argument a character or string specifying the alternative hypothesis. Either of, any one of two-sided greater or less should be taken. For mu is a number specified, an optional parameter used to form the null hypothesis. It is required for one sample test. Paired a logical indicator whether you want the paired test or not. For Wilcoxon sign test, paired should be true, and Wilcoxon Ranksum test, paired should be false. Exact, the logical indicating whether an exact p-value should be computed. Correct arguments asking for a logical indicating parameter whether to apply continuity correction in the normal approximation for the p-value. Conf.int, a logical indication whether the confidence interval should be computed, and conf.label, confidence level of the interval. The formula, if it is a formula format, then it would be the formula, say LHS, tilde sign, RHS, like this. And the data, then subset, if subset of the data you want to analyze, and na.action should be na.omit. And then finally triple not argument. Here is an example of one sample test. So Hamilton depression scale factor measures in 9 patients with mixed anxiety and depression taken at first X and second Y visit after initiating of a therapy administration of tranquilizer. Say X equals to this value, from that example it is taken, and Y equals to these values that has been entered. Then Wilcoxon.test, if you just pass X and Y, and here as it is a paired test, so paired equals to true, alternative equals to present, and then it will give you the V equals to 40, p value is 0.19, which is statistically significant. And alternative is less, you can change the less, or exact equals to false, correct equals to false. You can use the other arguments as you want. The Wilcoxon test, two sample test, for example, I'm taking this example from the same book, is this is say X and Y is two independent samples. Say X is the actually human Kuriomonian level X between 28 to 12 to 26 weeks gestational age, Y, and so Y is this and X is this, so that is entered. And then if you pass X and Y, an alternative equals to say greater G, then it will give you the alternative the greater than the right tail test, and W should be the 35 and P is 0.12, which is not at all significant. And another example that I am here giving the two sets. One is normal, generated from normal 10 and normal 10 with two standard deviation, two mean. So mean 2 and standard deviation 1, another is mean 0, standard normal distribution. And the confidence interval I am telling true. Then it will generate the confidence interval of the interval, that is say difference, confidence interval of the difference of these two variable, mean difference, and the difference is estimated as minus 1.86, and the confidence interval is minus 2.6 to minus 1.10, and the p-value is lesser than 0.001, so it is statistically significant. If somebody wants to use the formula format, so can use in this way, say Wilcoxon.test, ozone, tilde symbol, then month. So you want to test whether the mean ozone level varies across different months or not, and data equals to quality, and subset we can use that month. This is again the one binary operator, that actually the month it will take only 5th and 8th month, that is 5th and 8th month. So the results will come like W equals to 127 and p value is less than 0.001 itself, which is highly significant. The next test is a Kruskal-Wallis Ranksum test. Here, Kruskal-Wallis Ranksum test is mainly, as we learn, that Wilcoxon test for Wilcoxon Ranksum test is for independent t-test, and Wilcoxon sign test is actually for paired t-test. Similarly, the Kruskal-Wallis test is the generalization of independent t-test, that is, it is a non-parametric test of one-way ANOVA. So to perform a Kruskal-Wallis Ranksum test, and arguments that you have to pass is x, the numeric vector of data values, a list of numeric data vector, g is the vector or factor objects giving the group for the corresponding elements x. Formula, you can also pass through formula structure the way it has been shown for earlier functions for Wilcoxon test. Then data and optional matrix and data frame, then subset and optional vector specifying a subset of observation to be used. Na dot action should be na dot omit. I'm using this example here. It is a mucociliary efficiency from the same book, in that mucociliary efficiency from the rate of removal of dust in normal subjects with the obstructive airway disease and subject with asbestosis. That is the AX, say the normal subjects are 2.9, 3.0, 2.5, 2.6, 3.2, and Y is C 3.8, 2.7, 4.0, 2.4, and Z is C 2.8, 3.4, 3.7, 2.2, and 2.2, and these are the three variables. And the Kruskal-Wallis test can be performed with just list X, Y, Z. That is one way, and the Kruskal-Wallis chi-square value, that actually the large sample approximation by chi-square test here, the chi-square statistics here, and degrees of freedom equals to 2, p value is 0.68. This is one way of using Kruskal-Wallis test. Equivalently, we can perform in this manner is, say X is X, Y and Z in a one variable, and G is for indicating the group variables, so replicate and a factor replicate 1, 2, 3, 4, 5, 5 times, and labels are normal subjects, subject with obstructive airway disease, subjects with asbestosis. And Kruskal-Wallis test X, G can be put, and that will give you the result as the test statistic is 0.77 and p value is 0.68, degrees of freedom is 2. This is another way, and if somebody wants to use the formula format, you can use the same air pollution data and say write Kruskal.test, then ozone is a response, and month is a stratified variable. So ozone and then tilde symbol, then month, and data equals to air quality. That will give you the Kruskal-Wallis test results. This is a third way of using Kruskal-Wallis. Say here p value is much lower than 0.001, and the statistics Kruskal-Wallis chi-square statistics value is 29.266 and degrees of freedom is 4. These are the few statistical tests and non-parametric statistical tests I covered in this module. Few are still there that will be covered in the next module. Hope this will be very much helpful. There are many other functions available in R software, but you have to just look for R archives, and it might be different. It could be a different same test by different functions. This is by default. These are the functions that comes by default once you install the software. I mean, this is sufficient for doing the non-parametric test for difference. I mean, difference between two means or difference between more than two means. In this module, we have learned the application of non-parametric statistics in R, especially the sign test, the binomial test, the Wilcoxon test, Wilcoxon sign and sign test, and Wilcoxon Ranksum test, the Kurzweil-Wallis test, and what are the different arguments that need to pass through those functions are available in R, and how to interpret the results come out after after applying those functions over the real data.